Objective 3, Section 4.5. Sullivan's precalculus used the rational zeros theorem to list the potential rational zeros of a polynomial function. Let's think about this task that we have. First of all, we're trying to list potential rational zeros of a polynomial function. I think we feel pretty good about what a polynomial function is. What is a zero? A zero is a value of x. Okay, so it could be any number. Like 2 could be a 0. It's not just 0 that's a 0. It could be any number. Values of x so that when you run that number x through the function f, you get 0. Okay. What is rational? Now, what we're saying is we're going after numbers that make f 0, but that they are rational. And so that means they can be written as a ratio, as you might expect from the word rational. A ratio, integer 1 over integer 2, integer 1 over integer 2. If it can be written that way, well, what's an integer? All the whole numbers with the negatives. Okay. But if it can be written that way, then it's rational. And if it's a rational zero, then, and if it is allowed to be a rational zero by this theorem, that's what we want to list. So here's the statement of the theorem. Let f be a polynomial function of degree 1 or higher of this form. Well, what does this form mean? I mean, that's like pretty crazy looking. It just means it's a polynomial function. That's what that's saying, okay? But we do have to get comfortable with subscripts. Okay, each coefficient is an integer. It's a whole number or the negative of a whole number. If P over Q in lowest terms is a rational zero of f, then P must be a factor of A naught, okay, the constant, there's no x there, the constant, and Q must be a factor of the lead coefficient, A sub n. So any rational zero has to be of the form factor of this thing over factor of this thing. So for example, here's a polynomial function, and any rational zero will have to be of the form a factor of that over a factor of that. Okay. And what are these factors? What are these factors of the constant? Well, you know, a lot of things go into 12. And since we're going to be considering positive and negative factors, we don't have to worry about whether we have 12 or negative 12. But, you know, all these numbers go into 12. plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. There won't be as many numbers that go into 3, just 4 integers, 1, negative 1, 3, negative 3. Well, what we do is make all possible fractions of numbers from the P list over a number from the Q list. Okay, I kind of like to start with this and put everything over 3 and then put everything over 1. So put everything over 3, so plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 3 over 3, plus or minus 4 over 3, plus or minus 6 over 3, plus or minus 12 over 3. And then once I've put everything over 3, then I'm going to come back and put everything over the 1. Plus or minus 1 over 1, we already have that. Plus or minus 2 over 1, we already have that. Plus or minus 3 over 1, we have to list that because we don't have that yet. Plus or minus 3 over 1. Plus or minus 4 over 1, we already have that. Plus or minus 6 over 1, got to list that. And plus or minus 12 over 1, list that. So that is a list of all of the possible potential, according to the theorem, rational zeros. And if you do it that way, you take the larger Q and put everything over that, and then go back this way, put everything over the smaller ones, then you kind of get a smallest to tallest list. You know, we'd have to switch these, and that's what we have here, written smallest to tallest. Now, I don't know that it's necessarily a requirement to do that. Certainly wouldn't be on my test if this were a test problem, but it might be for my math lab. Actually, I like my list better than the one that the slide writer made, because he's got his fractions at the end. Anyway, if something is going to be a rational zero of this function f, then it is going to have to be on this list here of how many we have. 18 numbers. Any rational zero is going to have to be one of these 18 numbers. Now, it doesn't say anything about irrational zeros, and it doesn't say anything about any particular number on this list of 18. You know, you pick out any one of them and it may or may not be a rational zero. All we're saying is that this theorem allows that number to be a rational zero, and no other number but what is on this list.